Speaker Elaine from Marquette University, Wisconsin. A brief introduction about her. She did her PhD in Northwestern in applied math, and she was also a postdoc in SAMC with Chris at the same time as Amit Apte. And her now currently she is in Wisconsin. Her research interests are data assimilation and applied probability. And she is going to talk to us on a brief introduction to probability and simulation. Hello.
Yes. It says it's on. Okay. So I guess there's some of the things are similar in spirit to yesterday's talk, and some are a bit different. I chose to do the slides so I could cover a whole bunch of background to get everyone to have a similar vocabulary. So I'm going to go through a whole lot of information. I suspect many of you have seen much of it or parts of it. If you haven't seen it at all, I'll have Amit, well, regardless, I'll have Amit post this afterwards. So I would think if you're taking notes, the best thing to do is just sort of take notes to fill in the gaps, right? Not so much to write down the equations, because they'll be available for you. Okay, and we'll see where we get. There's a lot of information, so if we can't get to Monte Carlo today, we'll move that. Okay, so a basic review of probability. Basically, we think about probability, we have some events, and they have outcomes, so let's say E1, E2, et cetera. And associated with each of these outcomes is a probability. So they're going to be numbered associated with their event. And the probabilities go between 0 and 1. So not quite technically speaking, but practically speaking, if an event has probability 0, it never happens. If an event has probability 1, it always happens. And we have some notation here that the probability of event EK we call PK. And I don't want you to be intimidated by the number of slides. There's a bunch of overlays, so basically it's like 30 slides. Okay, so I'm going to go through some rules of basic probability. The probability of an event EI and event EJ happening is at most the sum of the probabilities of the individual events. Okay, and similarly, the probability of event EI happening or the event EJ happening has the same rule. So you think about this, right? You think about when you first start talking about probability, our tools are coins and dice, right? Coins and dice. So you can think about this. Maybe I'm interested in the probability of rolling a number greater than 2 and the probability that that number is odd. Or maybe I'm interested in rolling the probability, or interested in rolling a number greater than 2 and or that number being odd. So those, in some cases, will be different numbers, but these are the sorts of things we're thinking about. Okay, so we say that events EI and EJ are mutually exclusive if one happens means the other can't happen. Right, so we flip a coin. If we get heads, we can't get tails. If we roll a die, if we get a 3, we're not going to get any of the other numbers. And in this case, the probabilities reflect this idea. Oh, and I should say, just sort of to follow my notation, anything that's underlined for now, anything that's underlined is a definition. There's going to be lots of definitions because we're sort of starting from the very basics. So the probability, in a mutually exclusive case, the probability that EI and EJ will happen has to be 0. And the probability that EI or EJ happens is exactly their sum. Questions? So you can stop me at any time for questions. And maybe Farhan will say, oh, you should have some questions now, just to prep you because he was so good at it yesterday. Okay. Oh, so in another rule, I have these events, the probability that I have outcome E1 or E2 or E3, or if I go through the whole list of possible outcomes, the sum of those probabilities has to be 1. Right? And that means if we have an experiment, we have to have an outcome to the experiment. Okay. So now we'll think about compound experiments. So a compound experiment is a set of experiments with its own outcomes and probabilities. So now we're thinking about rolling 2 die, say. So we can consider an experiment with sets of events E, I, and Fj, and each of those experiments has their own probability associated with it. Okay, so the outcome is going to be a pair, EI, Fj, and it's going to have this joint probability Pij to describe the probability of that event. All right, so this is a really, I should have highlighted this. This is a really important rule, right? So we're going to have some more rules about basic probability. If the events are independent, that means that the product of their individual probabilities is the same as the joint probability. And this is a tool that we'll use all the time, right? This is something that ends up being really important. Okay. So now we're going to rewrite this joint probability, right? Yesterday, I think Varahan said something that I agree wholeheartedly with, that basically the tricks we have in math are to multiply by 1 and to add 0, right? And it's which choice of 1 and 0 you pick that make you clever, I guess. Okay, so here all we're doing is looking at our joint probability Pij and multiplying it by the sum. Oh, excuse me. So we have our probability Pij. We're multiplying it by the sum over the second index. We're multiplying it by the sum over the second index to hit the top and the bottom, so we're multiplying it by 1. And we define this sum over the second index to be the marginal probability that event EI occurs. So basically what we're thinking, so I have this joint probability, and I'm going to go through all the cases of the second event. Right? And if I add up the probability of the first event over all the cases of the second event, that's going to give me the probability of the first event. Okay, so here we have this notation, and then we're going to, it's instructive really to rewrite it like this, and that should be a small p. Okay, so the conditional probability, so we say the probability of event j given that event I already occurred, or event fj given that event I already occurred, is the joint probability of the two divided by the probability of E sub I. Right, so really what we're thinking is we'd like to know, we already sort of know the probability that the E sub I event, how much it's taking. So you really want to know the fraction, right, the ratio of those two to give us the probability of event Fj occurring given that E sub I already occurred. Okay, and combining these two from above, combining these two, we get that the joint probability we can write down as the probability that E sub I occurred times the probability that F sub j occurred given that E sub I already happened. We can also write this down in the opposite order. And we'll come back to this later, but this is really our basis for Bayes' formula. Okay. So everything we've been talking about to this point will applies sort of to anything random we're thinking about. But now we'll think about, we have these events, E sub I, and we're going to associate some numerical value with each event. When we do that, what we end up with is something called a random variable. Okay, so think about the expectation of a random variable. Well, I'm going to take all of the possible outcomes, right? So I roll my die, get 1, 2, 3, 4, 5, or 6. I'm going to weight them by the probability of each of those outcomes, and then add them together. This is our expectation. Right? This is what we call mean. This is what we call average. The possible x's we can take on. We've already heard some of these words, right? But I just want to make sure everyone has a firm understanding of what we're talking about. The possible x's that the random variable could take on, we call that the state space. Okay, so I have this case of rolling a die. The state space is all the numbers, 1, 2, 3, 4, 5, or 6. The probability of each of those is 1/6, if your die is fair, right? If you're an honest person. All right, so then we can just look at what the expectation is. And it's a little strange. When we're thinking about discrete random numbers, we can end up with an expectation that actually isn't in our state space, right? We don't have a face of the die that has 3.5 as an answer. And so sometimes when you see something funny, you have to think, well, is it reasonable, right? And that's reasonable, right? It's definitely within the minimum and maximum values in our state space. Right? If I told you that the mean was 10, you'd say it's crazy, right? And these are the sorts of things when you're getting answers you have to think about, right? This is a little strange because it's not in my state space, but is it unreasonable or not? Like those are the sorts of questions you always have to be asking yourself. Okay, so now if I have some function g, so g is just a function, right? It takes in a number, gives me out some other number. If I stick a random variable into that function, now g of that random variable is also a random variable. So we can think about its expectation, right? So now, whatever I'm taking the expectation of, each of the cases gets weighted by its associated probability p sub I, right? And then we add them all together. Okay, so here's another example. I'm flipping a coin. We have to associate some numerical value with the coin, right, for it to be a random variable. So normal choice is to have heads as 1 and tails as 0, or maybe heads as 1 and tails as -1, depending on the problem you want to set up. If the coin's fair, then each of the probabilities for each side is going to be a half. Now I have some function, and I'm going to stick all of my possible state variable values into the function and see what I get. Now for my random variable g of x, right, this is my state space. These are the possible outcomes. Right, and the expectation is just computed like before, right? So the expectation of the random variable x is a half. The expectation of the random variable g of x is 2.5. Questions? Comments? Okay. So here's another, right, maybe another thing I should have highlighted. Here's a rule about expectations that gets used all the time that's really important. Expectations are linear, right? So this is just our typical definition. So it doesn't have anything to do with expectation necessarily, but it's our typical definition of linear, right? I have some constants, alpha and beta. I have my two random variables, g and h. I have those constant times each of the random variables. Since it's linear, I can separate the plus, and I can factor the constants out. It's standard definition, but it ends up being something that we'll need to use to simplify things when we get to harder cases. Okay, so more topics, higher moments and variance. So now, right, this isn't actually really any different than we saw on the last page. I'm taking the expectation of some function. Right now my function is a random variable raised to the power n. Same definition for expectation. If n is the first power, I just get the expectation back. Often, when we're referring to a random variable, we say that the expectation of the random variable is the mean, and we usually call it mu. Okay, so you want to think about a central moment, right? That's when you're looking at how far away is the random variable from the mean. And how far away is the random variable from the mean? You can take this for any power of n, same definition of expectation, the probability times the thing you're taking the expectation of, adding up all the cases. And the variance is the case, right? The variance is the case when n is 2. So the variance of x is the expectation of x minus mu squared, right? Whatever you're taking expectation of, you multiply by the probability of that case and add them all up. We do some algebra. This is the sort of thing we could have for a homework problem. You know, you should do yourself to make sure you believe this if you haven't done it before. After some algebra, we see that this relationship for variance says that I have the expectation of the random variable x squared, which is also a random variable, minus the expectation squared of x. And the key, let me give you a hint, the key sort of to doing this is to recognize once you take the expectation, it's a number. Right? It's a number. We already had these rules about things being linear, expectations being linear and having sums. If I have some number, right? If I have some number, it doesn't depend on the index. I can factor it out. Yeah.
One question there.
Yeah.
Why we know variance is actually showing telling us how much
Okay, so it's telling you other things. So the third central moment is something called the skew, right? So it sort of tells you how much the random variable, or the distribution of the random variable, which we'll get to when we talk about continuous random variables, how much that's leaning to one side or the other. And effectively, if we have, and this isn't something I was going to get into, but effectively, if I had all of these moments, I could recreate the whole PDF. You can think of it sort of like a basis for any sort of function, right? If I had all of these moments, I could recreate the PDF. And if your PDF looks like a Gaussian, just has sort of one mode, you probably don't need very many moments to categorize it well, right? But if you get this sort of case where Chris showed yesterday, where you had this thing, the likelihood function looking like that, and you wanted a PDF of it, right, you would need many, many moments. And this is just a note that that if we're talking about the random variable being this function g of x, the same rule. Okay. This is sort of some consequences of independence. So here I have my random variables x and y, and we're thinking about these jointly distributed. I can look at the expectation of the product of those random variables. Again, it's the same sort of definition. I have this thing I'm taking the expectation of, weighted by the probability of that event occurring. Here I'm being a little sloppy with my notation. This is really a double sum over I and j. Right, a double sum over I and j. So I'm counting up all of these cases. If these random variables are independent, and that should be lowercase, sorry about that. If these random variables are independent, then I have this Pij is P1i times P2j. Right? That is the product of the marginal probabilities is the joint probability. So now, right, so I'm looking at this where I've plugged in this relationship. And two of these guys depend on I and two depend on j. Right, so I can factor the ones that don't depend on j out of the j summation. Right, so now we end up with this double sum, but each of these sums independently was just the expectation. Right, so we get this relationship. If these random variables are independent, the expectation of the product is the product of the expectations. Okay, so yesterday we talked a lot about covariance, so here's sort of a very basic view of it. Covariance is sort of a measure of independence. If I have the covariance of x and y here, it's going to be the expectation of the product minus the product of the expectations. Right, so we see this automatically. If they're independent, it has to be 0. Right, these are the same thing. And here's another case that gets used a lot, and when you haven't thought about it in a while, you think, why is that true? And this isn't like expectation, that expectation is a linear function, right? This is a special case. If x and y are independent, I can look at the variance of x and y, and that's defined to be the variance of x plus the variance of y. And I think this should be a minus twice the covariance of x times y. Let's see, do I agree with what I just said? I'll have to think about it, but regardless, if they're independent, the covariance of x and y is 0. Right, the covariance of x and y is 0, so we get that the variance of the sum of two random variables is the sum of the variance. If the covariance is 0.
If covariance is 0, then x and y are independent?
Yes.
Opposite?
If the covariance is 0, x and y are independent. Yes, I think that goes both ways.
Opposite always true. Opposite case is always true. Using it vice versa. X and y are independent. Then covariance of x, y is equal to 0. But if covariance x, y are different, can we say that x and y are independent?
I think so. I think that goes both ways, but I don't remember for sure.
It's not.
It doesn't?
Generally, it's not.
No, okay. Okay, so we'll say if we know that x and y are independent, then the covariance is 0. Okay, so now we'll move on to talking about continuous random variables. So we're thinking, letting x now be real valued, and we're going to define a continuous distribution function, which we'll refer to as a CDF, so it's going to be a function of x, right? So our state space here now, for most of this, we'll be thinking about the real line. Right? Our state space is the real line, and our CDF is the probability that a random variable is less than some number on the real line. So you give me any number on the real line that you like, and for a given random variable, we can tell you what the probability of being less than that number is. Okay, so some properties of CDFs. If the probability that x is less than x1 plus the probability that x is between x1 and x2, right, then if I'm in either of these cases, we have that the probability of x is less than x2. Right, and this goes back to that mutually exclusive thing. I can't be in both of these cases at once. Right? I'm either in this case or this case, so the sum of these probabilities is the probability that x is less than x2. Oops. This CDF capital F, is a non-decreasing function. Right, so it's going to be between 0 and 1 for all values of x. And it's going to be either staying the same or getting bigger. If our state space is the real line, at minus infinity we start at 0. Right? And this makes sense with our definition. There's no numbers that are bigger than minus infinity. And at infinity we're at 1. Say all of our random variables are less than infinity. If f is differentiable, then the probability density function, so this should be underlined. This is another definition, which we'll call the PDF, is defined as the derivative of the CDF. Okay, so here's an example. So we have a CDF. It starts off in green. It starts off at minus infinity 0. It never decreases. It goes up to 1. Right, and this blue function, the PDF, is the derivative. So this makes sense, right? We can see where the slope is the biggest, this function has maximum. Where the slope is 0, this function is, especially up here, this function is also 0. Now I'll talk about some properties and definitions of PDFs. So this is very much similar. Now I want you to think, going from the discrete case to the continuous case, as sums are analogous to integrals. Right? An integral is like a continuous version of a sum. So if I integrate my PDF, right, so the PDF is really telling me what is the probability that I'm in a certain region. Right? What is the probability I'm in a certain region? I have to be, my experiment, right, I have to be somewhere. I have to be in some region. So if I add up all the possible places I could be, I have to be in one of those places, so that has to sum to 1. And you think about that, this is like a probability, like a weight, so it doesn't make sense for a PDF to be negative. It doesn't make sense for a PDF to be negative. I want to know the probability that my random variable falls between two places, a and b. That's just going to be the integral from a to b of f of x dx. Right, so maybe here we could think about the probability that a random variable is between minus 5 and 0, and it's going to be this piece of area beneath the curve there. Right, so the mean is much like before, right? It's the same idea. I take all the values of my state space, multiplying by their associated probability, add them up, which in this case is integrating. It gives us the mean of a continuous random variable. And the variance here, we have the same idea, right? So I have the expectation of my possible states minus the mean squared. Right, and I didn't write this in, but I probably should have. Right, and I assume everyone knows this, but that the standard deviation is just the square root of the variance. Okay, so I have just a few distributions that come up a lot that are good to know. And all of these means and variances, Right? They can all be calculated like this. Okay, so here's a uniform distribution. Right, uniform really means evenly weighted. Right, so this is sort of the continuous version of our dice. Right, I'm going to pick a number evenly between A and B. Here's the CDF and the PDF. I'll leave it to you to calculate the mean and variance. Here's an exponential distribution. For an exponential distribution, our state space starts at 0. Right, so now we would think about our integrals instead of being from minus infinity to infinity would be from 0 to infinity, or you could chop this function off at 0, however you like to think about it. Here we have our CDF and PDF. Again, we can calculate the mean and variance. So normal distribution, right, we talked about a lot already. The CDF, right, if this was an integral we could do analytically, I'd have some function written down here. So it's not an integral you can do analytically. But I can take its derivative, of course, right, because I can always, right, that's the easiest derivative to take. I can differentiate an integral and end up with the PDF that I'm pretty sure everyone's seen before, which again has mean, mu, and variance sigma squared, which all of these, right, you can get by taking x times this f and integrating from minus infinity to infinity. Okay, so here's a sort of interesting case. This is if you're a mathematician, you would call this the Cauchy distribution. If you're a physicist, you might call it the Lorentz distribution. So here we have our CDF and PDF, and this domain we're looking at, the CDF still has a way to go to get to 1, right? And what that means is that there's still sort of a lot of mass in this tail. Right? There's still sort of a high probability that it could be way off here. And what do you think the mean of this is? I mean, what would you do if you don't know? Well, if I didn't know, so if I asked you this and you didn't know, what's the operation for the mean? So I just can't hear you guys. So I integrate. So I multiply this by x and integrate from minus infinity to infinity. I do that, and I have this integral that looks like x over x squared. I have an integral that looks like 1 over x. Does that converge? So the mean doesn't exist. If the mean doesn't exist, there's no chance. I mean, the mean goes into the definition of the variance, right? There's no chance of that existing. And so you could say the both don't exist, or you could say the variance is infinite. And this is the sort of thing, it's not so important that you know the Cauchy distribution necessarily, but it's important to know that these sorts of distributions are out there. So if you have some algorithm on the computer say, okay, I want to draw samples from this distribution and calculate a mean. And you say, wow, when I do this, my mean changes every time. Is that a problem with your algorithm, or is that a problem with your problem? Right? When you get something that looks strange, when you get an answer you don't expect, those are the sorts of things you have to ask yourself. Right? You say, oh, my algorithm's broken. This doesn't make sense that I'm getting this answer, that the mean changes every time I try this. Right? But you have to think about, is there a possibility that I'm applying this algorithm to a problem that doesn't make sense to apply it to? Right? And when you see answers that seem strange, this is the thought process you always need. Okay, so now to joint continuous distributions. So this is all analogous to what we've been thinking about. So I have a bivariate distribution function and a joint probability distribution function respectively. Right, so my joint CDF, right, is the probability that x is less than some number, the probability that y is less than some number. And now my joint PDF is going to be the second partial with respect to each of those variables. Okay, and here, so this is the same covariance matrix that we were talking about yesterday, right? So if you haven't worked with it before, this is what the definition looks like. So along the diagonal, I have the variance of all elements. So here I'm just thinking about two variables, right? Yesterday we had m, Right, yesterday when we looked at the observations in the afternoon, right, we had m variables, and we really wanted to think about how each of them were interacting. Right, so we looked at the covariance of each of the variables, and that's given by the same expression as in the discrete case. Right, so we're thinking about the expectation of the product minus the product of the expectations. If it's continuous, expectations are really integrals. Right, it's not so important that you write that down, but that's always what you want to be thinking about. We're always really, when we're thinking about probability for continuous random variables, we're really thinking about integration. Right, it's really just sort of grand integration problems. All right, so we have the same sort of idea of independence. If x and y are independent, then the joint distribution is the product of the individual distributions. So here I've just noted, just so we remember, the distribution that goes with x is 1, the distribution that goes with y is 2. We can talk about the conditional probability, so say the probability of y given x. Right, so we have the probability of y given x. That's the joint probability divided by this marginal probability. Right, so the joint probability of x and y, and the marginal probability of x. Right, so if we're integrating over y, the y variable disappears, and we end up with a function of x. Right, so we have this marginal probability of x here. If I want to take a conditional expectation, right, and I sort of want you to get thinking about it. This is sort of a very basic setup. I want you to get thinking about, sort of bigger problems. Right, yesterday, we were interested in sort of what do we expect to happen with the monsoons when we know there's been an El Nino. Right, so we know there's been an El Nino. How much rain do we expect to have? So this is just a definition of a conditional expectation. We have y, and we're thinking about the x is taken on some specific value, right? Some value we know. So we have y integrated against the conditional probability. I want to make sure that this is going the right way to think about it. No, I think this should be y against the conditional, right, because what we're interested in is this, we're interested in the expectation of the random variable y, given that x happens. So this should be the conditional probability of y given x. So, excuse me, should be flipped right here. So I'll fix these, especially if someone notes my mistakes. I'll fix them when they go online. Okay, so this should really be flipped. Yeah. Oh, sure. No one?
I think that's already there. No, so I think that's not how it's supposed to work, right? So there has to be at least
Okay. So back to this conditional expectation. So we have the integral of y. This should be flipped again. So the distribution of y given x. We can stick in this distribution of y given x, right, which we have up here. So now I have y integrated against, right, when I take an integral, it's a number, right? So this is a function here. This is a number, or it's not really a number because I'm taking the integral on y, so I get a function of x. But as far as y is concerned, that's a number. Right, so I'm integrating this thing against y. Really, I only have to worry about the top function, because that's the only place that y shows up. So we get this expression, and now this whole thing is a function of x. Right, and that makes sense, right? What do we expect y to happen given that some x happens? Well, it depends on what x happened. Right, so we expect that to be a function of x. And now this looks a little crazy, but what if we take the expectation of this thing? Right, so I have this expectation of y given x is a function of x. So I'm taking the expectation of this. That means I'm taking the expectation of it with respect to x. So I'm integrating against the marginal distribution of x. But what I have on the bottom is the marginal distribution of x. Right? So that's the marginal distribution of x. So those guys cancel, and now we have this double interval of y versus versus the joint probability. If I do the integral in x first, then I get the integral of y versus the marginal probability of y, which gives us the expectation of y. Okay, so I'm dropping the 1 and 2, but I'll know if there's an x inside, that means a distribution with respect to x. If there's a y inside, it means a distribution with respect to y. So here are definitions of marginals. If we rewrite this conditional probability from the last page, so let me go back. Right, so I'm going to rewrite this. So I have the probability of y given x is the joint probability divided by the marginal. Okay, so I want to rewrite that. So basically, I have the joint probability divided by the marginal. I multiplied the marginal over. Right, so I have the joint probability is the conditional probability of y given x times the probability of x. And it goes the other way too. Right, so the joint probability is the conditional probability of x given y times the probability of y. And now both of these things equal the joint probability, so they have to equal each other. Okay, so they equal each other. And now I'm going to divide through by the marginal probability of y. Right, and this is something that it's important to think about a little bit. It's important to think about a little bit that this thing really should be the integral of the top, right? And is that the case? It is, right? So if we go up here, we can see that y is the integral of f of x, but f of x was exactly our top, right? And this brings us to what we saw yesterday, Bayes' theorem. Right, we have the joint probability of x given y is proportional to the probability of y given x, which we often call the likelihood, times the probability of f. And Chris said something yesterday that I think is true in spirit but not in practice. Right, really what we care about the proportional because we care about where things are happening, where this probability, where the modes are big. This sort of Bayesian perspective being practical really didn't catch on to the last 20 years or so. Really didn't catch on to the last 20 years or so because because to actually write down this distribution, well, I had this complicated distribution I came up with, with all my models and data say, and to actually write down a function, I had to be able to integrate it. I had to be able to integrate this thing that was awfully hard to come up with in the first place, right? And so when we were trying to do things analytically, Bayesian ideas are just very, very difficult.
Given x, probability of x given y is equal to probability of y given x divided by probability of y.
Right.
And if you get the proportion, doesn't that mean that 1 by probability of x y is equal to constant?
So say the last part again.
If we see these two equations, one is equal to and one is proportional.
Right.
Doesn't that become a constant?
Yes, it does. And and it was this integral. Right, it was this f of y is this integral. So it is this it is effectively a constant of proportionality, but to actually write down an expression and use it, I would need to be able to figure out what that looked like. Right, so before computational Bayesian methods were developed, it was you had to only work with very special cases. You could actually sort of do these integrals. come up with those normalizing factors. So it's not that, I mean, Chris is right in spirit that you really care about where things are happening. But in practice, this wasn't a very practical tool until 20 or 30 years ago. Okay, so Bayes' theorem and data assimilation. Right, so X are state variables or model variables we were thinking about yesterday. Y are observations. F of X is our prior distribution. F of Y given X is our likelihood of an observation. Right, so how likely is an observation compared to all the possible state values? And F of X given Y is our posterior distribution. And this is really what we're interested in. How probable is the state given the observation? Right, how probable is that we'll have rainfall below 10 centimeters below average, given that there was an El Nino? Right, so our goal is to know this posterior distribution. Right, that's really the goal of data assimilation. And if we really sort of, we'll accept knowing less than that. But if we know this distribution, then we can answer any question you ask. Right? And really, our options here are to sort of assume everything is Gaussian, and then we have products of Gaussians or Gaussians, and it's very tractable. Right? It's very tractable. It's something you can work with easily. Or to try to do some sort of approximation of this posterior distribution with sampling. With sampling this distribution over and over and over again to get a sense of where the mass is, where do the samples hit. Okay, and so how do we sample this posterior distribution? So this is sort of back to the themes of yesterday. We have to crawl or walk before we can run. Right, so now we're just going to talk about, we're going to change gears and just talk about how to sample a distribution. Right, so again, we're not thinking about moving from this slide on, we're not thinking about X and Y being state variable and observations, they're just variables. Okay, so basically our strategy is to use uniform distribution to generate random variables from an arbitrary distribution. We're always going to have access to numerical, to the computer telling us uniform distribution between 0 and 1. Right? If it gives us between 0 and 1, we can get it between any A and B we like. Although we're really interested in it being between 0 and 1. How this works is probably a whole nother lecture. But they're based on something called a linear congruential generator, or sort of families of that are more sophisticated now. But we're going to assume we can access uniform random variables in MATLAB, or C or Fortran, whatever you like to program in. Okay, we want random variables distributed according to some, and now we're thinking about this as a given distribution. You give me a distribution, I'll hand you a random variable. Right, so you're right now, you're thinking about giving me a function. You'd like random variables to come from that. Okay, so we're going to let the distribution, so Q is the one you gave me. X and Y are just arbitrary variables at this point. P we're going to say is a uniform distribution. So really what we're looking for is some sort of transformation from X to Y that if I draw X from a uniform distribution, Y comes from the distribution you want it to come from. Like that's our goal. That's what we're looking for. And so I have to use this rule that basically says, well, if I want to go from X to Y, if I want to go from uniform to some other distribution, I have to take into account sort of how their differentials are related in 1D, right? And it's analogous in multiple dimensions, but we'll just think about 1D. So this is what we're going to use, and we're going to assume that P is uniform. Okay, so this is what we're looking for. We're looking for some function G to relate X and Y. It's equivalent, and really this is kind of what we're looking for ultimately. We're looking for some other function G inverse that relates X and Y. Right, so I have X is some function G inverse of Y. I'm going to differentiate this function with respect to Y. All right, so I get this dx dy needed in that rule. I get that dx dy needed in that rule from the last page. which is just going to be the y derivative of this function. Right, so we had this from the last page, but p is uniform on 0, 1, so p is just 1. Right, our weights are just 1. They're just even on 0, 1. So what we get is q of y is 1 times this derivative. But this derivative, right, was the derivative of this inverse function, g inverse of y. Okay, so q is a known function, and it's a known function, and it's a derivative of the function we'd like to know. Right, so if I have a function that's the derivative of the function I'd like to know, what do I do to it? Integrate it. Right, so we're going to integrate this. Right, and maybe you had a hint because it was in the title. We're going to integrate that, which is the same as integrating this inverse function, which is the same as integrating dx dy with respect to y. These last two, right, these last two are both going to use the fundamental theorem of calculus. Right, an integral of the derivative is just what's inside. So what we're going to have here is that g inverse, right, so the y integral of the y derivative is going to be g inverse. I have the same thing here, I have the y integral of the y derivative of x. So g inverse of y is x. Now if you know the function q, and you actually did the integral, you get this. Right, so now this is something you know, something you've written down, and so now you can take the inverse. So now we have this relationship that says, well, if I draw a uniform random variable here, this is going to be distributed according to q, which is any distribution you handed me. Okay, so say this is the distribution you handed me. All right, so and what do I mean? I want to sample from this, right? Really what I'm looking for, and I sort of intentionally left off labels. I don't like leaving off labels, so I think it's bad practice. But the inverses get confusing, so I intentionally left off labels. But here, when I say sample this, I'm looking for values here. Right? I'm looking for these x values, and I expect a bunch of them to come where I have these modes, and not very many over here. Right? So really what I sort of think is just collecting a bunch of x values, maybe a couple on the edges, but mostly where the modes are. Okay, our algorithm says, well, we have to integrate this thing and invert it. So, but this is a PDF, so our integral is a CDF, right? Because the derivative of a CDF was a PDF. So we have this CDF. It's actually, if you had the CDF, you wouldn't have to go through this step. And really, I sort of want you to focus on this picture, because really what we're doing is we're going to be sampling this uniformly. It's sampling this uniformly. I come over to this relationship, and it's going to give me samples from Q. Right, but because this is an inverse function, we can't plug in the dependent variable, right? So we have to invert it. So this is just the inverse of this picture. Right, so now our algorithm says if this is uniformly distributed, then these are going to be distributed according to Q. Right, so what do? I had MATLAB hand me a uniform number. Let's say it's right here. I go up to this relationship, which I have written down pencil and paper, and I said, that gives me minus 4. Right? I want more of these random variables. I'm greedy, I do it again. Now it gives me one here, gives me a variable there. And what I'm collecting ultimately are numbers along this line. They're going to be distributed according to Q. So this is the sort of the basis for everything. The problem is often you can't integrate Q. Sometimes maybe you can integrate it, but you try to invert it and it's hard. Maybe you could do it, but it seems too hard. In multiple dimensions, this would be nearly impossible to proceed. But the idea is going to be the same, right? The underlying idea is really what we're interested in. And this is really sort of the crux of it. Often you don't have an analytic expression. I can't hand you a Q for you to integrate and invert and then give me random variables back. I might not be able to write it down, right? And this, you say, well, that seems crazy, but this is exactly what we're doing in data assimilation. Right? right? I have some initial conditions. I run them forward in my model, and I get this prior distribution at time t1, right? All I've done is sampled this. I don't have a formula for it, right? So Chris mentioned yesterday, to try to write down formulas for this to move forward, they get very ugly very quickly. Right, so typically we're not going to have formulas, so what do we do? Right, what do we do? And sampling is just a really important idea. And the first solution is rejection sampling. And here, we're actually thinking that we have some expression for Q or some knowledge of Q, but this is really the basis for any other idea that you're going to see, like this idea of rejection sampling. Okay, so suppose we want to generate random variables from Q. Integrate and invert doesn't work. Our trick is to choose a function, f, where f is always greater than or equal to Q. And f is a function you can integrate and invert. Right? So it's not quite distribution, right? Because it's always going to be bigger than this one, so I wouldn't expect its integral to be 1. Right? Otherwise it would be Q exactly, and that's not something we can work with. So it's going to have some integral that, if we chose well, is finite, and we'll say it's A, some number A. And then we can sample from this thing that's like a distribution using our integrate and invert method. Right, so we're sampling from this thing that's like a distribution. It's really the probability density of f of x normalized by A, right? Whatever its area was. So this is our strategy, and I want to sort of go through the algorithm. And I have a picture that sort of shows the whole algorithm. I think it might be useful to draw out the pieces of it, though, because the picture is really busy. So we're going to select a uniform random variable in the range of 0 to A. Right, and the idea is going right back here. Right now this function doesn't go up to 1, right? It went up to something bigger than 1. It went up to A. So we're going to select a uniform from 0 to A. We're going to find x, that's our g, that there's this transformation to get the uniform from f. X is going to be g, where we constructed it from the last page. Now the next step is we're going to choose another uniform that goes, and now this is a number we have. Right? We selected a z, we have it. We plug it into our function, we have x. F is a function I can plug into, so now this is a number we have. So now we're going to select a uniform in that range. And the key is, if y is less than q, we're going to accept x, and x is going to come from this distribution q. If y is greater than q, we're going to reject it. We're just going to repeat. Right? And the probability of acceptance really looks on how close was this distribution, the sort of fake distribution that we sampled from, how close was it to the one we wanted? And this is what the picture looks like. But I can actually probably even get the colors if they work. Let's see. So our first step, we have this, that one's not very good, but that's all the red I need anyway. We have this PDF that we know how to invert. Right, we know how to invert it. And that doesn't look. And it goes to this green number. And since it's integrated to 1, it's not going up to 0, it's going up to A. Right, that's going to asymptote to A. So now what we do is we pick a uniform. We get a black one too. I know they're really faint. We pick a uniform number somewhere in this range. Right, we call that Z. Now we go over to the function we could integrate and invert to its CDF, and we come down and we get an X value. Okay, well I don't need those colors anymore though. Okay, so now we get this x value, and now what we want to do is pick a uniform in this range from 0 to f of x. So we pick a uniform random variable in this range, and let's see, we pick a uniform random variable in this range, and let's see if we can look from here, and we come back over. I should probably draw it over here. That makes more sense, right? So we pick a uniform random variable in this range. We come back over, and we see where this puts us. Let me back up. Okay, so we have our uniform from 0 to z. But we come back over. So I'm adding a step I shouldn't have. Then we have this uniform we're picking between. We have this uniform we're picking between 0 and f of x. And now this is really to see, am I above or below this function we're interested in? Am I above or below that function? If I'm above it, we reject it. If we're below it, we accept. Right? And you can see, right, if the red curve was closer to the blue ones, when we were choosing between the axis and the red curve, well, if the blue cursor was close to it, we'd probably be below the blue curve. Right, so when you're doing this, you want to sample from a distribution that you can integrate and invert, but that looks like the distribution that you're interested in. Right, that's the goal. Any questions on this? This is an important idea. Going once? Amit? Sorry, I can't hear you.
Both the samples. You're choosing the first sample from the uniform.
Right.
Then the second time you sample, it's also from the
Right. But they're different uniforms. So the first one, they're both from uniforms. Right.
It's the same as saying generate a random variable restricted to that.
Yes.
Generate a random number restricted to that.
Right. A uniform random number restricted to that interval. Yeah. Right. So we need these two uniform random numbers. The first one is really to get us to do this integrate and invert and get us a candidate. So we have this candidate variable x, and then we have to say, well, when I plug in to my function, when I plug into my function, was the random variable here bigger or smaller? Right? Should we have kept it or not? Other questions? Comments? Okay. And in some ways, this idea is very straightforward, but it's tricky until you try it yourself. Right? So you guys will be trying this yourself for sure. Okay, so sort of, I think yeah.
What I always have trouble with when I see this is where this sort of brings us at the end. You're kind of collecting x's by this process, right?
Right, which is the goal.
Process, you collect x's, and that somehow gives you an idea of the distribution,
Yes.
right? By digging.
Right. Okay, so that's a good point. So this is giving me x values, and I'm going to get more where my Q curve has these modes. Right, but it's giving me these x values, and if I get a whole bunch of them, then we can bin them, right? So basically, we'll split up our domain into little boxes, and say I've done this 100,000 times, right? Then I'm just counting how many of those fell in each of the boxes along here. And what I'm going to get, yeah. that's true. Okay. If I get 100,000 acceptances. Yes, so that's a good point, right? Because I'm not.
In this case,
Right. You throw it away. Right. Right. And really, right, that this 1 over A is sort of, it's the ratio of this area to that area, right? So the closer those are together, the more we're going to accept. Right? And this is actually a good check on if your routine's working. Right? You can count how many you're accepting. Right? And this is something you certainly knew how to integrate. Right? So we can know what our acceptance rate should be. Because we'll know A, so we should know what the acceptance rate should be. So we'll say we've done this and we've accepted 100,000 samples. And now I count how many are in each of the boxes. Sure.
suppose you reject an X.
Yes.
Does that mean the rejection we never considered again? Then suppose what you do, you can considering a value between 0 to fx.
Mm-hmm.
Suppose another time the same X, you find another Y.
Right.
Y selected for which the condition holds.
Right.
Right. So that you can accept that.
Yes, you would. And so there's some subtleties there. You're never, because this is continuous, you're never going to draw exactly the same X twice. But say you drew something super, super close, so effectively the same. It might be, then it depends on your Y. But you'd want to accept some of them, right? Because there is some mass here. Right? So sometimes when I was near here, I'd want to accept it. Right? And how much I want to accept it depends on how far away the curve was from the distribution I actually found my X by. Yes, that was a good question. Any other thoughts? Yeah. Oh.
Say without the rejection sampling, just the sampling from the uniform, and then you want to map to a variable that you want. Does it also work for variables which do not have mean? So, for example, Cauchy. If you found, so can you sample Cauchy distribution by using this
Yes.
either the previous one or this one or both?
You can.
Okay.
You can draw samples from a distribution that doesn't have a mean.
Yeah, and but how do you check the convergence of that?
Okay, so this is sort of goes to an in practice thing, right? So in practice, you would do a histogram, say, and then you would also, and you have to be careful with it because you have to include cases that might be far away because you might be sampling way into the tail. And then you might want to do something like a chi-squared test. And if that doesn't mean anything to you, don't worry about it. But just a sort of statistical test to say, does this seem to be working? But there's no, that I know of, there's no rigorous way to check.
Okay, and so effectively, this could be done for any distribution in practice.
Yes.
Or it does not necessarily need to have a mean or variance or higher moments or any of that.
No. This can certainly be done for heavy tail distributions.
Okay.
Right, so distributions that have a lot of mass in the tail are called heavy tailed, and maybe they'd have a mean but not a variance in higher moments, or maybe like the Cauchy they have none of them. But you can still draw samples from them. So, and that might be useful. I mean, maybe that's what your data looks like, right? I know some people work in finance, and that this idea of heavy tails is very common. That it's these sort of crazy outlying events like mortgage bubbles, right? That really dominate the behavior, right? And so if you see that's what your system is doing, you want to simulate it, then you're going to want to draw random variables from that sort of distribution. Yeah. Yeah. This one? yes, so for Cauchy, yes. Sorry about all the overlays. For Cauchy, yes, because we have this inverse. So we have this, so we can invert it. And it's actually an inverse function, so this is an easy thing to invert. So it's something that you should be able to do. If you can do the integral, we have these non-decreasing functions. That doesn't mean there's not some place that's flat that might interrupt here, just for a completely arbitrary distribution, that might interrupt your inverse. But generally, the inverse, if it's an increasing function, the inverse should exist. If you can actually do it is a different question. And this is also sort of another point that's not something I meant to talk about, but it's really important, is that if you take a transformation of a random variable, you're probably not going to end up with the same random variable that you started with. Right? I mean, maybe you will, but in practice, I would assume that you wouldn't. For some arbitrary transformation, if I start with a uniform, I wouldn't expect a uniform. Right? If I start with the Gaussian, I might not expect a Gaussian. Right? And it's not so much that, and those can be very hard problems to figure out what that looks like, but it's important to know that's something to worry about. Right? That if I have a Gaussian and I transform it, I might end up with something very different. Right. Yes. Exactly.
And so always x is simply cumulative.
Right. Right.
So x always function g of x always exists. For any distribution for
Right. Yeah. Any other questions? So, yes, I'll see. I guess see if we should. And these sorts of methods are really the basis for more sophisticated methods. Like Amit does something called a Markov chain in Monte Carlo, which is really sort of based on this idea. It's really based on this idea. It's a Metropolis Hastings, which it will be used in a Markov Monte Carlo simulation. Yeah.
So there's no x and the one factor. The y values are just
The y values are do you accept or not?
are used to test.
Yes.
The x is not converted yet.
Then they can run away. So I don't know anything about this sort of myself, but I've heard that if you're sampling something and the rejection rate's very high, right, and you want to distribute this among a bunch of computers, then keeping track of those y's that you're rejecting actually becomes useful information. But the details I don't know. More questions on it? Okay, so I guess the sort of in some sense, if you bin this and you have this estimation of the distribution, that gives you everything you want, but the questions you're really answering are often sort of less information than the whole distribution. Or you want to know that the probability that there's 10 inches less of rainfall than normal, given that there was an El Nino, right? So if I have a probability, right, so I have my distribution here, what did I call it down there? I called it Q of X. Right, so then really what I'm interested in is this integral I don't remember what the numbers were, but let's say rainfall 10 centimeters less than the average, given an El Nino. Right, so you're interested in this probability. If this is your distribution, if this is this marginal distribution, then really what you're interested in is integrating this from 0 up to this value. Right, so often the questions you want to answer are integrals. If you have the whole distribution, you can answer any question you like. And this gets us into the idea of Monte Carlo methods. So I guess I'll leave this choice up to you. There's technically like 2 minutes left and there's 10 slides. So I could move this to next time or I could keep going. Do you have a preference? Huh? Move it to next time? Okay. That's fine. Oops. I guess I can take any other questions though that have been stewing before I close this.
How do you know when it's facilitated? In this process, presumably you would let the bins get narrower and narrower, and then you would do more and more samples.
So there are statistical quantities you can calculate to see if things are reasonable. So basically, what you're interested in is if I just think about one bin. Let's put down my marker. If I just think about one bin. So this is, say, the ith bin, and I'm just interested in the samples that fell in here. And I can think about the mean of the samples I shouldn't say this isn't the mean, this is the sample mean. Right, so Ni is the number of samples that fell in the ith bin. Right, and then I'm just taking the average of those numbers. So I can calculate that, and I can calculate something analogous called the sample variance. Right, so just for the samples I'm taking, right, just for samples I'm taking, and how much do they vary? And if you have that this ratio of the mean to the sample standard deviation stays in check, so this is something called the coefficient of variation. If that stays in check, that's a sort of good indication that things are going well. So I mean, in some ways, one of the hard parts and one of the sort of not something to overcome, but something you have to be incredibly careful about is if you're doing, in one dimension, you can bin it, you can look at it, you can be pretty confident, you can check your acceptance rate, you can be pretty confident you know what's going on. If you go to really high dimensions, well, maybe you have some information about the state space, and you say, over here in state space, this is where things are very probable. I'm going to focus my samples on this probable region of state space. I'll sample from it. I'll look at my coefficient of variation. Things will look good, right? That stays relatively small, relatively stable. I'm sort of getting what I expect. That doesn't mean, but right? That doesn't mean that there isn't some sort of disjoint region of state space that there's another mode, that there's some relatively, maybe not as big, maybe 10%, but still something that would contribute, right? So you have to be sort of very careful to have a sense of the physics or the modeling or something to tell you where in state space you should be looking when you're really sort of targeting samples specifically, right? Because when you can sample a line, when we get to Monte Carlo, we'll talk about this. You can sample a function off of a line, no problem, right? That's a very doable thing. But when you go to really high dimensions, you have to think about how to distribute the samples around all dimensions, right? And really what you're interested in doing is sampling this Q here in this region, right? This is what you care about in your integral. You don't really care about the probability that this was 10 centimeters above. That's not the question you're asking. Right, so if you know the question and you understand the model or the physics behind it, you can get an idea of where in state space you should be looking and sort of focus your samples there. And this idea of focusing samples we'll talk about next time. Yeah.
Data coming generated from various institutions or sources, like from the satellite or from the synoptic station data, or meteorology or atmospheric data. Can this rejection sample method be useful?
I don't.
Garbage or false or bad data, as we say, comes, and you have to reject or the quality control.
I don't know. I don't know. I've never heard of it used in that sort of setting. Something I'll talk about next time would be very useful. And that sort of, you have a sample of data and you'd like to know if the estimates there's this thing called bootstrapping. You'd like to know if the estimates that you're taking from your data are reasonable, right? And this is something we'll talk about next time. But as far as rejection sampling, I've never heard of it being used or those sorts of more sophisticated sampling methods. I haven't heard of it being used in that context. It doesn't mean it doesn't happen, I just haven't heard of it.
How do you fix the EM? Coefficient of variation increases with EM. Accuracy.
I actually would think, so if you're getting more samples, right? So actually, this is something that you would be monitoring as you took samples, typically. So you think about this as a function of n, and this is a number that should be stable, should be around 1 or less. And if you look at this as a function of n, if you have some instability in that function, that should raise alarms. That should raise alarms. So yeah, this is actually something, for the first few you might ignore, but once you get to a sort of a large quantity, as you add more samples, and what that would say, what would make this very different, potentially, what could change this mean and the variance relatively, if there was some other region of state space you sampled, and maybe we're thinking about this random variable being a function of something else, and it landed you right here. Right, and then that could look very different. But these aren't proofs or anything. This is just sort of the quality control you do for the algorithm. Other questions? Yeah, Amit. Okay.
There must be
Yes. Yeah, I can't think of a reference off the top of my head, but I can find one. Yeah, no. Probably in Gardner's book, yeah. That's a good book in general. So I would think there was some of this. I'm not sure about that, but There's it's actually another book I'm thinking of. I'm not thinking of the authors.
Tell us later, but that would be useful probably.
Okay, yeah.
There is an engineering book titled Beyond Problem Filtering, Optical Filtering by 3 authors. Extremely good engineering approach to sampling.
Okay.
Beyond Problem Filtering.
Beyond common filtering. There's a book on particle filtering that came out around 2000 or 2001 by this DeFreitas and someone else. That's sort of but that already sort of starts knowing this stuff, right? So it's not. So you would need something a little more basic. Other questions? Huh? A comment?
Something like this. Doing sampling some distributions that
Yeah.
or it goes to a big anti-tuning design, doing the convergence of
Have you talked much about the projects yet, or no? Okay, you're not yet. Is the plan? Okay. All right. And I promise for my other talks there'll be much less information, and we can spend more time focusing.